Hi everyone, thank you so much for joining us today. Uh, we have with us a guest speaker, uh, Hasan Kader Hammoud. He is a PhD student at King Abdullah University of Science and Technology, working under the supervision of Professor Bernard Ghanem. Hasan has worked in multiple topics such as robustness, 3D understanding, LLM agents, and continual learning. In this session, he will be talking about the latest research, which deals with the Pretraining, data diversity for self-supervised learning. Thank you so much for your time and overview.
Yep. Thank you, Ahmed, for the invitation. So today I will be presenting my work titled on pre-training data diversity for self-supervised learning. This was a collaboration between KAUST and University of Oxford during my internship at Oxford. So first of all, a big thanks to everyone who's been part of my life so far. In terms of advising, I joined KAUST in 2021 as a PhD student. Before that, I was a master's student, and then I did an internship in Oxford with under the supervision of Philip Tor, Hadel Bibi, and Fabio Pizzetti. And now I'm at Samsung Research under the supervision of Umberto Micheli and Matteo Zai. And this work was produced basically in this phase of my life. Okay, so self-supervised training, if we look at the most important intellectual breakouts according to Jan LeCun that happened in the last 10 years, the first one of them is self-supervised learning. And why is that important? Because self-supervised learning means that we have a data set, we have no labels, and we can get so many samples that are unlabeled from the web. And then we want to train a model using some task that is agnostic of the labels. It does not require any labels to train. And we see that there are two major components in a self-supervised training pipeline. The first one requires data. The second one requires computation, basically compute. And of course, given that you don't have labels, you would expect that you need a lot of compute to let those models converge in general. All right, so let us look at the reasons behind the success of SSL algorithms. The first thing you can spot is a lot of compute, 4096 V100 GPU days for SEER, one of the big papers in self-supervised training. And the next component is, as we said earlier, is data. And we find that they used around 1 billion images. And if we think about 1 billion images in terms of tokens, assume you have patches of 16 by 16, a regular VIT, and your images are 224 by 224, you would end up with something around 0.2 trillion tokens. And this is somewhat similar to what people use in LLMs, right? Like 1, 2, 3, 6 trillion tokens, and so on. Probably at a slightly smaller scale. All right, but there's a big question here. So what matters more? Is it this large amount of compute we're throwing, or is it the large amount of data we are putting there? And to answer that, this is why we have this paper, and this is quite an important question to ask. All right, so one important thing to note is that if you have a computational budget, it directly means that you have a budget on your training data, like a budget on the data. Why is that? So let's say you have 1 million samples, but you only have enough training budget to train on 100,000 samples, then it inherently means that you're bound to 100,000 sample training and not a million. So budgeting compute is directly budgets your data. Okay, so in this paper, we're trying to answer two major questions. The first one is, given a computational budget, should you train on more diverse samples for less epochs or less diverse samples for more epochs? So basically here we're looking at, should you train on 1 million images of ImageNet for 10 epochs, or should you train on 100,000 images for 100 epochs instead? And the second question is, how does the selection of your upstream data affect your performance on the downstream tasks? So let's look into some kind of important terminology. So computation budget in this paper is defined not as flops, but rather as the total number of scene samples. So given your data set, let's say you have 50,000 samples, and you have 10 epochs, then you have effectively a total of 500,000 samples to see. So all methods, or in the same table, methods are given equal amount of total number seen samples. This is one part of our normalized evaluation. So again, the example, Cypher 10, 50K samples. If you train for 10 epochs, then your budget is 500,000 total scene samples. Okay, the next thing we define is data diversity. And here we define data diversity as the ratio of the total number of samples over your compute. And what does that mean? It means how diverse is your training. Your training. So let's look at a simple example. You have Cypher 10, 50K samples. If you train on them in one epoch, then your training was super diverse. Basically, you only saw each sample once. You never did any repetitions, and this is diversity 1. Whereas if you train for 10 epochs, then those samples have been seen more than once, and therefore you get hit on your total diversity. And this is due to repetitions. Okay, and one last thing to define is what's upstream and what's downstream. So an upstream is simply your data set where you don't have any labels, you're doing your self-supervised training on. Whereas in your downstream, now you have a task of interest. You have this model that you trained on a billion images without labels, but you want to tweak it to your task. So my task of interest is classifying flowers or ImageNet classification, and I have a supervised objective. So those images have labels, and now I can actually train with labels. All right, I promise we are ready to dive into the paper. So the first question that we're going to ask is regarding performance as we increase the number of samples. So does collecting more samples from the same distribution, and same distribution here means the upstream and the downstream have the same distribution, help in pre-training given a fixed computational budget? Okay, so what does that mean in terms of visually? You take the flowers dataset or your ImageNet dataset or whatever dataset, you remove the labels, do SSL on it, and then plug in back the labels and fine-tune your pre-trained backbone. So we take different fractions of Cypher 10. So this is Cypher 100, 50K samples. You can subdivide it into 5,000, 25,000, 50,000. And of course, as you increase the number of samples, you are only allowed less epochs, and this means less diversity. So less samples equals to less epochs, less diversity. Sorry, more epochs, less diversity. Okay, and the compute is always fixed. So whenever you want to change the number of seen samples, you increase your epoch such that you maintain this fixed computational budget. And what do we observe? That if you have as you have more samples and hence more data diversity, training with less epochs would give you better models. And this is consistent not only in Cypher 100, and it's also consistent in Tiny ImageNet, and it's also consistent across columns. So it means different methods, all of them exhibit the same behavior. Whether it's SimClear, Biol, Suave, whatever method, it's the same conclusion. And this insight is summarized here, where we say when the distributions of the upstream and downstream are the same, so your DSSL and DTask are exactly the same, then, and in a normalized computational budget, you're better off increasing your data diversity, reducing your epochs for an effective training strategy. But then you would get another question here, which is, okay, what happens if our upstream and downstream are unknown? We don't know what's our upstream and downstream, and we want to increase our data diversity, right? So I'm training for a task that I don't know yet. I will know the downstream in the future, and I want to increase the data diversity of my dataset. Again, we have several options here. Assuming that you know the upstream and downstream, you know that they are the same distribution, then one option is if you had a goldfinch, hornbill, anemone as classes, then you would also augment with similar classes, either from an existing dataset that was previously curated. Let's say you take Tiny ImageNet, half of it, and then you augment it with the other half, and this is what we did here. Or you can simply go over the internet and crawl a bunch of images, or get a diffusion model, run a diffusion model, generate images, and augment them to your training set. However, there's something important here. All of those assume class priors. They assume that you know the classes in your dataset. And this is not true. This is only possible for controlled settings, but in actual scenarios, you would not know the downstream classes ahead of time. And here we bring in a note that there's one SSL technique, which is pretty famous, DynoV2. They do assume knowledge about the downstream, and therefore it might be an unfair advantage. And we will discuss this in a few. Okay, so in reality, you should not assume class priors. Instead, you can augment your base dataset with classes that are randomly selected. So you can select Japanese spaniel, ibex, squirrel monkey, collect samples from existing datasets, or web crawl to get the samples, or again, use generative methods. And what do we observe? We observe the following. So first, the black dashed line is the line before adding samples. So you take 100,000 samples, you train, and this is your line. And the bars are after augmenting with another 100,000 samples collected from different sources. So you start with your base, and then you union the base or augment the base with another source of data. And what we notice is the following. Generally, if you have no classifiers, so out of distribution, more or less synthetic web and source perform similarly in some methods. So in Biol and Sinclair, they are super similar. And even in Barlow-Twins, it's not really that big of a mountain. However, we do experience something where, in that case, augmenting with more samples hurt the performance on the downstream. So this tells us that you cannot simply go ahead and just augment whatever samples and say my SSL training will improve on the downstream. This is not true. The second point is that if we look in the case of in distribution, it's almost always the case that you can improve over the dashed baseline, which is your original trained model, without augmenting. And we noticed that the general ordering is that synthetic performs worst, and then web and source kind of perform similar, but there is a small gap between source and web. And of course, this gap is expected. Images that are collected from ImageNet are center cropped, and they are collected from 2009, 2010. And therefore, there's a time distribution shift where when we collected our samples, it was 2023. There's a time distribution shift. So if an image in ImageNet, okay, you had images of laptops, those laptops are 2009 laptops or 2010 laptops. But in 2024 or 2023, things look distributionally different. Plus, when you collect samples from the web and you don't do any curation, you might have some kind of noise. The images are not center cropped, and this is expected. Okay, and this brings us to the second insight. The second insight is basically when the distributions of the upstream and downstream tasks differ. So your DSSL and D task are different, and you are in a computationally budgeted setup where you have a fixed compute. Increasing your pre-training diversity may harm your SSL pre-training performance. So as we observed, out of distribution almost always hurt the performance. And this means you cannot simply go ahead and say, oh, I'll just go collect samples, throw compute, and improve performance. This is not true. Okay. And for the last question that we propose in this paper is, how do the previous observations and conclusions hold at scale? So all the previous experiments were done on a budget which is kind of not too big. And here we want to move to bigger data sets. And we consider two data sets, YFCC 100 million, which is collected from Flickr. It contains a lot of images of places and so on. 98 million samples. We fix a budget of 98 million total scene samples. And you are allowed a total of one epoch over YFCC 100 million. This is the budget that we define. Whereas on ImageNet, if we look, ImageNet has 1.28 million samples. Given a budget of 98 million, which was defined for YFCC, it directly means that you can do 77 epochs over ImageNet 1K, assuming you're training on all of ImageNet 1K. And this is what we observe on Sinclair. We had other methods as well, Moco V3, Dino, several methods in the paper, but let's zoom in on one of them. So again, one epoch, 98 million samples. This is the YFCC line. There's nothing too scary about the numbers seen in the columns for ImageNet. It's just taking different partitions of the dataset, 10%, 20%, 50%, and 100%. And what we notice is that generally, the performance of ImageNet is better than YFCC by a big margin. So if you look at ImageNet, 7%, or here you have around 9%, 8%. It's quite a big gap, except for places where the performance is, in that case, better for YFCC training and slightly worse for FITB. And this brings us to an interesting question. Is there anything unique about places? Is there a distribution shift between the upstream and the downstream that could quantify this observation? So keep this point in mind. We will go over this next. Okay, so the last insight that we have in this paper is even an extremely large data diversity cannot mitigate the distribution shift under normalized computation. So even if you get YFCC 100 million, incredibly high diversity, you will not be able to simply say, I'm going to bridge the distribution shift between my upstream and downstream. And this kind of enforces the importance of having SSL techniques that effectively use those large-scale data sets to learn some unique representations. And again, large data sets cannot mitigate the distribution shift under normalized computation. Okay, so first question is, why does YFCC do super well on places but not on everything else? We go ahead, we just compute the visual DNA metric and the FID score, which are both metrics to measure the similarity between distributions. And what we notice is the following. For all the data sets, except places, the FID score is better for ImageNet, but not YFCC. But for places, the distribution shift or the distance between your pre-training dataset and your downstream dataset is smallest for places. And this kind of justifies why we had better performance for places, or somewhat very competitive performance. Okay, and then let's think about it. What can one take from this ablation? Can we design methods that collect samples from the web that are closest in FID or visual DNA to the downstream task? So let's say you're working in the medical field, you have images of X-rays, and you won't find so many X-rays on the internet. Is there a way you can train maybe an RL agent using PPO or some technique in order to minimize the distance, the FID distance or visual DNA distance between your downstream and collected upstream on the run? So you go ahead, you leave your agent, go on the web, query Google, query Bing, whatever search engine. It will go collect samples, and you will reward this agent every time it gives you a data set which is closer in terms of FID or visual DNA to your downstream. Because if you can find such a subset, you can probably pre-train on this data and improve your downstream performance more than random collection of data. The second ablation we did was basically what happens when you do pre-training on YFCC with various diversity ratios. And what we find is that at a certain point, which is 0.01 or 1% or YFCC, which is a million samples, you pretty much saturate. There's nothing more that could be offered by this data set. And so there seems to be a saturation, and it would be very interesting for future directions for people to explore how can we detect this saturation. Is this saturation simply because this is as much as we can learn for those downstream tasks given the distance that we have defined earlier? Okay, so one last point is regarding Dino V2. So Dino V2, very famous paper, they trained on 157 million samples, different data sets. But if we look at the training data, let's look at the data sets, Caltech, DTD, aircraft, whatever. There are a bunch more. I just took this because it's interesting. And we look and compare to the evaluation, we find food is common, aircraft is common, DTD is common. There are so many common data sets that are used in the evaluation and in the training. And this brings us back to the point that we discussed earlier, where we had class priors. If you assume class priors, which is what this paper did kind of, then you will see things that are kind of expected. You have improved on the distance between your upstream and downstream, and of course you will see improvements. And if we want to think of it in terms of future directions, one important thing that people should consider in the literature is, can we take this one step further, and instead of just budgeting based on the total number of scene samples, could we budget based on the flops? So we know simply is a very, very simple method. Dino is more complicated. Moco V3 is probably more complicated. Can we even budget it further to be also on the number of flops exhausted by those methods? The second point is, can we look into those algorithms that will go scrape the web, collect samples that minimize distance between upstream and downstream, such that we can get data sets that are more likely to work for our downstream, similar to the medical data set example I gave earlier. And another thing is, can we enforce evaluation with disjoint sets between upstream and downstream? So if we look at Dino V2 pipeline and try to update it such that we remove any overlap between your upstream and downstream, find some subset of classes which is completely disjoint, and we reevaluate all those methods that had the upstream and downstream distributions the same, or they had some kind of shortcuts where they assumed class priors. Would we see something different in terms of method performance or data efficiency? And the last point is on data efficiency. So we should kind of evaluate methods based on how good they use data. So we found that maybe SimClear is not very good at using YFCC 100 million. In our experiments, Moco V3 did slightly better, but it's still not, it doesn't outperform ImageNet. So it's quite important to also evaluate data efficiency of methods, like how good do they utilize different data diversity budgets. And finally, I would like to thank Ahmed Anis for this invitation, my co-authors, Tuhim, Fabio, Friptor, Adel Bibi, and Bernard Ghanem for helping out in this work. And we are open for questions if anyone has anything to ask.
Thank you. There are a few questions. There's a question in chat. So, question is, are augmented images?
I think you're lagging, Ahmed. I can't hear you. Oh, who's out?
Sorry, I got disconnected, and now I cannot see the question anymore.
All right, let me take a look at the questions. Maybe if someone asks something, you can. I think I only see one question, which is, are augmented images considered repetitions? No, in that case, we do not consider this as repetitions because this is inherently how the method works. But this could be one additional thing to take into account. So you could kind of think of, oh, if you have augmentations in your contrastive pipeline, then this is part of the budget. But since we define it as the total number of scene samples, then if you're augmenting the same sample twice, so let's say you're doing SimClear, you take a crop from here, crop from there, you augment it, then it's kind of still the same ratio of augmentations to the number of samples. So you can eliminate this factor. Okay, so what's the point of training on the same upstream and downstream? This is a good question. This is what people typically do in SSL training. I also agree that this might not be the case in general. There are a few papers that have shown that this might give you a boost on your downstream task training, or you can use some kind of supervised contractive loss instead. But yes, this is the general evaluation pipeline where you would find people reporting same upstream, same downstream to see how good your pre-training task without labels was able to extract features.
For example, your model can see fixed number of images, and if you are adding more data, then I think it was in the question one which you shared in the slide. So
Yes.
does this mean that when you are training with you are removing some of the images from the old data set, or because model has to see which number of images, or are you reducing the number of epochs?
No, you reduce the number of epochs basically. So if you have
I see.
5,000 samples, then it means you do 10 epochs. If you have 50,000 samples, you do one epoch. So usually, if you have 500 annotated images, then yes, you would want to do pre-training and then you would do fine-tuning. This is why SSL is important, because you can pre-train on many samples that you have not seen, learn a visual encoder that's very strong in terms of extracting general features, which are representations that probably could serve on your downstream task. And then you would do either linear probing, which is fix the backbone, train a linear layer, or you would do a little bit of fine-tuning on top of the model on those annotated images. So the idea which we spoke about, where you can look at an upstream that might be suitable for your annotated images, is something that might be interesting when you have very few samples. And this is the case in medical images. So there's one paper which is relatively recent. It was an IT oral, if I remember well, and it's called Internet Explorer. And they kind of tried to address this issue where they had an agent, it scrapes samples, they try to reinforce, like give it a reward based on how useful were those samples for the downstream. But instead of doing it based on FID, they did it based on you train the model on the samples, evaluate, and give a signal, which is very expensive. Um, so usually augmentations would help when you have very few samples. But in the case of pre-training, augmentations are just part of your pretext task, which is your task that is agnostic of the labels. I'm not sure if this answers your question.
I have another question. What is the pre-training task that you are using? Like, is it a single task, or are you using a combination of multiple tasks?
So for us, it's a single task. So when we're doing ImageNet, for example, you're trying to just use SimClear, which is a contrastive loss, or Dino, which is based on positive pairs, or whatever your SSL technique does exactly, and you're doing it on learning general representations for images.
Right.
I have a question.
Yeah, sure.
So what about like so you were saying right in the beginning, like less data, more data, like versus epochs. But let's say if you give more data, but what about the overfitting, right? So is there a chance of because the more data the model sees, the chance of overfitting higher, right? Compare.
Yes.
So did you guys come across that scenario where overfitting?
So in our case, we did evaluations all that, like we did intermediate evaluations every few epochs to monitor if any overfitting happens. It didn't happen really. Usually this wouldn't happen on this large scale data sets. Plus, in self-supervised training, it's less likely to overfit because you don't have labels to overfit to. So unless you're doing a very gigantic number of epochs over the samples and you have low resolution images, then you would probably overfit. Otherwise, it's just unlikely to overfit.
But may I beg to differ, because I have deep learning, right? Okay, I understand LLMs get self-trained, but in deep learning, when you feed the data, so even the deep learning models do overfit, right? That's why we have these regularization dropout techniques to. So I kind of disagree on that. Deep learning models do also get overfitting, right?
But they generally overfit when you give them labels, because when you give it a label, it's easier to overfit. When you're looking at patches of images which are augmented every time, it's less likely to overfit. And therefore, usually you would see this overfitting or label memorization in supervised training where you have a label. But when you remove the label, you're trying to learn something that's agnostic of the label. So it's kind of harder to draw. It's harder to segregate, create a decision boundary that will separate all the images. Plus, after you do your SSL training, you will do downstream probing, right? If you're doing probing, which is the common evaluation, you will only train a linear layer, and it's very hard to overfit a linear layer in that case.
Okay, so overall, you didn't see much of the overfitting problem.
No.
Which is good anyway, right? That's good. That's good.
Of course, of course.
Cool. Thanks.
You're welcome.
But actually, one more question.
Yep.
This what are the paper, right? Does it apply to large organization because they don't care, right? Let's say large organization, tech, whatever, big companies, compute is not a big deal. Data, like you said, if there's a big budget, big dollar, big data. So these applies only small organizations or small enterprises compared to large enterprises.
Of course. So one thing that we found out, if you remember in the second observation, if your downstream and upstream are of different distributions, we found that augmenting more samples hurts the performance. So in that case, big companies, regardless, even if they can throw compute and throw data at it, if your data is not suitable in terms of distribution to your downstream, then it will hurt your model, regardless of how much compute you have and data you have. So it boils down to distribution shifts as well.
I see. Okay, sounds good. Thanks.
You're welcome. Anything else?
If you don't have any other question, I think we can complete the section.
I have one question.
Yeah, please proceed.
Yeah, so I'm actually looking into fine-tuning a model that's been trained on large image sets, but fine-tuning it on a kind of a variation of the original set, a subsampled variation of the original set, say something like a masked version of it. How do you think this relationship would work out? Your hypothesis would work out in that case. So let's say if I trained on something like the pre-trained on ImageNet, and then I have some sampled it for say some N categories of ImageNet, and
yeah, in that case, you're operating in DTask and DSSL being very similar, right? So if you do pre-training on full ImageNet and then without labels, of course, and then now you're trying to fine-tune on a subset of the labels of ImageNet, then yes, this would definitely give you an advantage because you've already seen the classes in pre-training. And this takes us back to the first question, which is, if upstream and downstream are the same, then yes, more samples in general would improve your downstream performance.
so also my samples on the fine-tuning side are not exactly copies of ImageNet, but rather a transformation of ImageNet. So let's say if it's just segmented out objects from the image, and that's what I'm trying to learn representation for. Do you think like the diversity equations would still hold, or like how would you say plan the data sets for the downstream task?
I would think it would still hold, and the reasoning is the following. So we know that if you take a feature extractor, which is a pre-trained backbone, you've pre-trained on some data, you can tailor it. You can do some kind of fine-tuning to make it a segmentation model eventually. Like you can train for a segmentation task. And since you're already starting from a point which is closer to your downstream in terms of distribution, than compared to training on let's say images of buildings or houses, and then you try to do animal classification, whether your downstream is classification, segmentation, or object detection. And the NSSL is trying to get general backbones that can extract features. So let's say the contour of the objects would, in your segmentation map would still look something similar to what the feature extractor would extract over those images, right? So in that case, you still have a smaller distribution gap in terms of feature extractions.
Okay, got it.
Thank you.
Thank you.
Thank you very much for your time. It was really an insightful session.
Thank you.